Okay guys, in the last video we proved two properties of the wave function. The first one is like the value of y at t, at a particular t, at fixed t. At fixed t is the same value, at x, x plus lambda, x plus 2 lambda, and so on. And similarly y at fixed x has the value, has the same value, at t, t plus t, t plus 2t, and so on. What it means, like y at x over t equal to y at x plus lambda over t is equal to y at x plus 2 lambda over t, and so on. And similarly y at fx over t is equal to y at fx over t plus t is equal to y at fx over t plus 2t is equal to, and so on. These were the two properties we proved in the previous video. Now I'll come to another property. We know the frequency f, which is represented by this symbol f, which is equal to the reciprocal of time period. And also we know that speed of the wave, which is equal to the distance traveled, which is wavelength, divided by the time taken, which is the one period. This is the wave speed. Also we know that what we call it, wave number k, which is equal to 2 pi over lambda. From this we get the value of lambda, which is 2 pi over k. And similarly the angular frequency omega, this is the angular frequency, which is equal to 2 pi over f. So this implies that 2 pi over t, sorry, not f, 2 pi over t. This implies that the time period will be equal to 2 pi over omega. Now putting this value and these two value in this value in this equation, we get v is equal to 2 pi over k over 2 pi over omega. Now 2 pi cancel with 2 pi, so we left with v is equal to omega over k. But omega, v is equal to omega over k, this is one expression for the velocity. This is another expression. And also we know that v is equal to what we call it, lambda over t, which I can write as 1 over t, and 1 over t is equal to frequency, so v is equal to f lambda. This is another expression for the velocity. Next we will move to the transverse components of velocity of sinusoidal wave. The velocity of the particle, this was the velocity of the wave. Now velocity of the particle, which we represented by Vy, which is equal to dy by dt. Now y, which I already wrote, is a into sine kx minus omega t. Because this is omega t. Why it is omega t? Because we already wrote it is a is equal to sine a into y is equal to a into sine kx minus t. Yes, kx minus its value is, let me check it. I can write it as y is equal to a into sine 2 pi x over lambda minus t over t. So this will become equal to a into sine 2 pi over lambda into x minus 2 pi over t into t. And we define omega, the angular velocity, like k is equal to 2 pi over lambda and omega angular frequency is equal to 2 pi over t. So the wave expression will become a into sine kx minus omega t. For this I replace it by k, this one I replace it by omega. So now y, which is a function of, which is equal to a into sine kx minus omega t. So v of y, which is d over dt of y, and y is a into sine kx minus omega t. So this will become equal to, I'll bring a outside, and this derivative is acting on this function sine kx minus omega t. So the derivative of sine is cos kx minus omega t, and then we have again derivative of this, so we have minus omega. So from this we get the transverse velocity, or the velocity of the particle of the medium moving in a direction opposite to the wave is minus a into omega into cos kx minus omega t. And the transverse component of acceleration is, which is a of y, which is dvy over dt. If we differentiate this again, we get a with a negative sign omega square sine kx minus omega t. But we know that minus omega square a into sine kx minus omega t. Now this factor is itself y, because we already mentioned that y is equal to a into sine kx minus omega t. So here I replace this by this y. This is the transverse component of acceleration of the particle. Now we already wrote a general expression for the wave function, which is y, which is a function of both position and time, which is equal to a into sine kx minus omega t. Like what we did in the simple harmonic motion, we put a extra factor here, kx minus omega t minus phi here. This phi is the phase of the wave. Its value does not affect this equation. If we expand it, we get the same equation again. So here we call it this kx minus omega t minus phi is called phase of the wave. This is called phase of the wave. Like if two waves are moving, are said to be in phase if they have same motion. Like if this is one wave, and we have another wave moving such that their movement is same, then they are called in phase. But if two waves have different motion, like if this is one wave and this is second wave, they have a different phase because this point is not exactly at above this point. So there is a difference between these 2 points. So they are called out of phase. So next we have the group velocity. What we call, how we can define a group velocity? Group velocity can be defined as group velocity. The velocity of the information a message in a wave is called group velocity. As we know that a wave is a disturbance in the medium due to which energy transfer from one medium to another, one point to another point. So basically the transfer of energy, it means the transfer of some information. The information can be in any form. So the velocity of that information or the message which is carried by this wave during its motion from one point to another point is called group velocity. Next we have dispersion of wave. Dispersion of wave. Now the spreading of wave into its component is called dispersion of wave. Like if we pass a white light from a prism, then this white light is spread divided into 7 different colors. We see 7 colors on the screen. So this division of this light into its component is called dispersion of wave. In the next video we will discuss another type of we will discuss the speed of wave on a string. Thank you.